Hello everyone, welcome to my channel Dr. TAPATI'S presentation. Myself Dr. Tapati Vanjade. In this video I am going to discuss about pseudo-order reaction. We will know what is pseudo-order reaction, expression of pseudo-first order reaction, graph of a pseudo-first order reaction, examples of pseudo-first order reactions, and we will solve a problem associated with pseudo-order reaction. The meaning of pseudo is being apparently rather than actually as stated, or you can say not genuine. Now, what is pseudo-order reaction? A chemical reaction shows an order which is experimental value different from the actual order, that is theoretical value, when one of the reactants is present in a large excess. So when in an experimental condition, one of the reactants is present in a large excess, in that case a chemical reaction shows an order different from actual order. In that case, the experimental order, which is not the actual one, is referred to as the pseudo-order reaction. So, that experimental order is called pseudo-order. Consider this reaction where A and B react to form product B. Theoretically, rate of the reaction should be K into concentration of A into concentration of B. Powers are 1 and 1 for both of the reactants. So overall order should be 1 plus 1, that is equal to 2. Now consider an experiment where A is equal to, concentration of A is equal to 0.1 molar and concentration of B is equal to 1 molar. At the time when the reaction are about to go to completion, remaining concentration of B is equal to 1 minus 0.1 molar, that is equal to 0.9 molar, or we can say it is equivalent to 1 molar, which is the initial concentration of the B. That means we can consider B remains constant throughout the experiment. In this experiment, concentration of B is very high. It is 1 molar as compared to concentration of A, that is 0.1 molar, and therefore concentration of B remains constant. Rate of the reaction will be A into K prime, where K prime is equal to K into concentration of B power of 1, and concentration of B is constant, K is also constant. Therefore we have denoted K into concentration of B is equal to K prime, that is the pseudo first order reaction constant, rate constant. Therefore the experimental results will show overall order of 1 instead of 2. Experimental order is 1, but the expected order of the reaction should be 2. Therefore it is a pseudo first order reaction with respect to A, because concentration of B is very high. Therefore rate of the reaction is not at all dependent on the concentration of B. It is dependent on concentration of A only. Similarly, if concentration of A is in large excess, that means concentration of A is much greater than concentration of B, the reaction is considered as pseudo first order reaction with respect to B. In that case, rate of the reaction will be dependent on concentration of B, not concentration of A, independent of concentration of A. Expression of pseudo-order reaction. In Unit 10, I have discussed about the second order reaction kinetics, where S and S prime are two substrates, they are or reactants, they are converted to product P. In that case, if concentrations of S and S prime at time t is equal to 0 are A and B respectively, and concentration of each substance that has reacted after time t is equal to x, then remaining concentration of S and S prime will be A minus x and B minus x respectively. In that case, you can write initial concentration of and initial concentration of S and S prime are A and B, whereas final concentration of S and S prime are A minus X and B minus X respectively. When A is not equal to B, that means initial concentration of S and S prime are not equal. In that case, we can write this equation for second order reaction, that is log A minus X divided by B minus X, that is equal to A minus B kt divided by 2.303 plus log A by B. Or we can write it as ln A minus X divided by B minus X, that is equal to A minus B kt plus ln A by B. Now, if you write S instead of S and S prime, if you write reactants as A and B, in that case, if A and B are two reactants, they are converted to product B. In that case, you can write this equation again as ln A minus X divided by B minus X, that is equal to A minus B kt plus ln A by B, where we can write it as ln A by B, that means final concentration of A by B. You can see A minus X is the final concentration of A, B minus X is the final concentration of B. Here mentioned, already it is mentioned, so we can write this equation as ln A by B divided, that is equal to A0 minus B0. How? A0 means initial concentration of A. Initial concentration of A is A and initial concentration of B is B0, or we can write it B. In that case, we are writing as A0 minus B0 kt plus ln A0 by B0. We are just converting this equation to this equation. Or simply we can write it as 1 by A0 minus B0 into ln A by B minus ln A0 by B0, that is equal to KT. So here we are converting previous equation to this equation. Now again we can write it as very simple form, 1 by A0 minus B0 ln A B0 divided by B into A0, that is equal to KT. Now, if A0 is much greater than B0, we can write A0 as concentration of A. That means when initial concentration of one of the reactants, here A is the reactant, initial concentration of A is very high as compared to concentration of B. In that case, we can write this equation where A0 minus B0, we can write it as only A0, or as there will be no change in the concentration of A, or negligible change in the concentration, initial concentration of A. In that case, we can write A0 is equal to A. Hence, we are writing, converting this previous equation to this equation. 1 by A into ln B0 by B. Why? As A is equal to A0, you can cancel them, and therefore 1 by A into ln B0 by B is equal to KT when A0 concentration is much higher than B0. Or we can write it as B, concentration of B is equal to B0 into e to the power minus A KT. Or you can write it as B is equal to B0 e to the power minus K prime T. Why? Because A concentration is constant. There is no change in concentration of A. So we can write concentration of A and K is constant, that is K prime, and K prime. In that case, we can write this previous equation into this final equation, which is B is equal to B0 e to the power minus K prime T. Similarly, we can convert A is equal to A0 e to the power minus KT, or A is equal to A0 e to the power minus K prime T when B0 concentration is much higher than A0 concentration. In that case, B0 is equal to almost B. Initial concentration of B is equal to final concentration of B. So in this equation, A0 is the initial concentration of initial concentration of A. B0 is the initial concentration of B. K prime is the pseudo first order reaction rate constant, K prime. And K is the second order rate constant. So second order reaction rate constant. A is the concentration of A at time t, and B is the concentration of B at time t. Again, I am writing this equation. A is equal to A0 e to the power minus K prime t. Now, by taking natural logs on both sides of the pseudo-first order reaction, pseudo-first order equation, we get ln A, that is equal to ln A0 e to the power minus K prime t, or ln A by A0, that is equal to minus K prime t. It is a pseudo-first order reaction equation, where B0 concentration is very high as compared to A0. Let's estimate half-life of a pseudo-first order reaction. Half-life refers to the time required to decrease the concentration of a reactant by half. As I have shown in my previous slide, that a pseudo-first order reaction equation is ln A by A0, that is equal to minus K prime t, where B is in excess and therefore B remains constant, and B is equal to therefore initial concentration of B. If we put T is equal to T half, because we are calculating T half value, half-life value, and at that time concentration of A will be half of initial concentration. So we can write ln A0 by 2 divided by A0, that is equal to minus K prime T half. We are putting A is equal to half A0 and T is equal to T half in the equation of pseudo-first order reaction. Now we can calculate T half is equal to minus 1 by K prime into ln half. We are getting this ln half from this equation, this part. that is equal to 1 by K prime into ln2, because minus ln 1 by 2, that is equal to ln2, or we can write ln2 by K prime or ln2 by K into concentration of B, because I have told that K prime is equal to K into concentration of B, that is equal to ln2 by K into concentration of initial concentration of B, because as I told, B is equal to B0, so we are replacing B to B0 here. This is the half-life of a pseudo-first order reaction. So half-life of a pseudo-first order reaction depends on initial concentration of the B that is in excess in the reaction. This is a graph of pseudo-first order reaction where we are plotting concentration of A versus concentration of A versus time, or we can plot concentration of B versus time, and we will get this type of graph. Now I am giving two examples of pseudo-first order reaction. First one is hydrolysis of ethyl acetate. This is the reaction where it is ethyl acetate. Hydrolysis is going on. So ethyl acetate is reacting with water and it will produce ethanoic acid and ethanol. Ethanoic acid or acetic acid and ethanol. So hydrolysis of ethyl acetate results in the formation of ethanoic acid or acetic acid and ethanol. In this case, rate of the reaction should be K into concentration of ethyl acetate into concentration of water. It is the expected rate of the reaction. However, concentration of water is very high. Hence it remains almost constant during this reaction process. So we can write concentration of water is equal to constant. At that case, rate of the reaction will be K prime into CH3 C00C2H5, that is ethyl acetate, K prime into concentration of ethyl acetate, where K prime is equal to K into water. K into concentration of water. So this is the actual experimental rate of the reaction for the hydrolysis of ethyl acetate. Therefore, it is a pseudo-first order reaction. The power of ethyl acetate is 1. It is independent of concentration of water. So, it is pseudo-first order reaction with respect to ethyl acetate as reactant. Therefore, hydrolysis of ester is a perfect example of pseudo-first order reaction. Hydrolysis of water. In this case, water is present in excess. Second example is hydrolysis of sugar or sucrose. Hydrolysis of sugar or sucrose results in glucose and fructose formation. Here you can see this is an equation. This is an equation for sugar hydrolysis where C12H22O11 is the
formula for sucrose, and it is water. Hydrolysis is going on, and glucose and fructose are produced during the hydrolysis of sucrose. In this case, expected rate of the reaction should be K into concentration of sucrose into concentration of water. These are two reactants. So expected rate should be this. Now, however, the concentration of water is very high. Concentration of water is very high, and hence it remains almost constant during this reaction. So we can write concentration of water is equal to constant. Therefore, actual rate of the reaction will be K prime into concentration of sugar. Only rate of the reaction will depend on the concentration of the sugar. There will be no change in the concentration of water, almost no change. And here K prime is equal to K into H2O. K is constant and water concentration is also constant. Therefore, we are denoting it as K prime as constant for the pseudo-order reaction. It is a pseudo-first order reaction with respect to sucrose. This is the pseudo-first order reaction, example of an pseudo-first order reaction with respect to sucrose. Let's solve a problem associated with pseudo-first order reaction. This is the question. In a sugar hydrolysis reaction, following results are obtained. This time is at 0 time, t is equal to 0. Concentration of sugar is 0.50. When time is t is equal to 30 seconds, at that time concentration of sugar is 0.3 mole per liter. So it is a pseudo first order reaction. The question is calculate the pseudo first order rate constant for the hydrolysis of sugar. Let's solve it. Now we know that equation for pseudo first order reaction is ln A by A0 is equal to minus K prime T, or we can write K prime is equal to minus 1 by T into ln A by A0, that is equal to 1 by T ln A0 by A. We can write in this. So if we put A0 is equal to 0.5, A is equal to 0.3 and T is equal to 30 seconds, then we will find that K prime is equal to 1 by 30. We are putting these values in the equation, in this equation. So we will find K prime is equal to 1 by 30 ln 0.5, that is the value for A0, divided by 0.3, that is the value for A, is equal to 1 by 30 into 0.51. This is the value for ln 0.5 divided by 0.3. So if you multiply, we will find 0.02 per second. Unit of rate constant is per second. So this is the final result for the first order rate constant for the hydrolysis of sugar. Thank you very much for watching this video. Kindly like, share and subscribe this channel. Don't forget to press the bell icon to get the notification for new video.